So, right, this next video, again, this is going to be part 2 of the nervous system. Right, I kind of broken it up. The first video we had gotten through looking at neurons and how the different parts of the neurons, right, from the soma to the axon to the dendrite, right, what those different structures did. But then we carried on into the different divisions of the nervous system and how neurons and nerves are kind of compartmentalized, or how they are divided into these more specific groups of nerves. Right, there was the cervical plexus, the brachial plexus. Right, if you haven't watched the first video, you'll have no idea what I'm talking about. Here's where we're going to start to look at the actual spinal cord itself. Right, you can see all of the all these different nerves. Right here where they enter into as well as exit the spinal cord. Right, these are the spinal nerves. Right, I call those the on-ramp and off-ramp. Right, for instance, if you want to get into or out of the spinal cord, you have got to enter into one of these spinal nerves. At least that's the case for 98+% of the nerves in the body. There are a small group of nerves which do come directly out of the brain. Right? For the most part, most of them exit and enter the spinal cord via the spinal nerves. So, again, this here, right, this is just kind of a section of the spinal cord, and that's what we're going to start to get into here in this presentation. So, some of the different structures. Okay, so out here, the spinal nerve. Right, we see it right here. That was all these different spinal nerves which come out through here, through here, through here. That's what we're looking at. Now the spinal nerve. The spinal nerve is actually a combination of two things. Something called the ventral root and something called the dorsal root. This here, that's the ventral root. This here, that's supposed to be an arrow, which is awful. Right? That's the dorsal root. When they combine, they form like a Y. Right? The dorsal root here combines along with the ventral root here, and they form the spinal nerve. Right? Different types of information, so whether it's sensation or motor, travel through the dorsal root and ventral root. We will talk about that next slide. Here, I just want to look much more at some of the kind of macro characteristics of the spinal cord. We can see, for one, right, this, when you look at it, it looks like there's multiple layers, right, almost like it has multiple coats, right, one here, a second one here, a third one here. This outermost covering, this outermost layer, is something called the dura mater. There's a something called the meninges. There's a group, pia mater, arachnoid mater, and the dura mater. Those are the three layers which make up the meninges. Now the meninges surround both the spinal cord as well as the brain. By and large, help provide protection, but the other part is they help to encapsulate the brain and spinal cord in something called cerebral spinal fluid. A little bit later on, probably not today, but we'll look at cerebral spinal fluid and what it does and how it comes to be. But this outermost layer, all out through here, is the dura mater. That is unbelievably dense, tough, connective tissue. Very, very dense, very thick. Just beneath that is something called the arachnoid mater. The arachnoid mater. Now, there's spaces in between these. Right? Think of it. Take put an undershirt on, then put a t-shirt on, then put a jacket on. That jacket's the dura mater. Right? The t-shirt is the arachnoid mater. The undershirt is the pia mater. And you can imagine how there's spaces in between each article of clothing. Right? There's a space between your jacket and your shirt. There's space between your shirt and your undershirt. Right? Those spaces, depending on where it is, if it's beneath the dura. For instance, if it's between the dura and the arachnoid monitor, so if it's between the jacket and your shirt, that's something called the subdural space. The next space is beneath or deep to the arachnoid monitor. It's something called the subarachnoid space. Right, something called the subarachnoid space. Now, there's not a sub-PO space. As far as the PO monitor, there's not like a sub-PO space. Right, the PO monitor is a layer which is adhered like directly to the actual spinal cord itself. Right, so it's not so much like a layer that you can remove per se. It's adhered directly to the spinal cord. So some other structures that we see, right? One of the things when we look at all of this vasculature, right, the veins and the arteries through here, right, you can see they run within the subarachnoid space, right? They run deep to the arachnoid monitor, right? Spinal cords, blood vessels, CSF, right, cerebrospinal fluid, all of that runs through the subarachnoid space. To provide more kind of stability, support, right? We can see there are these what are called denticulate ligaments, right? These through here, here, here. Again, these help anchor the spinal cord to the monitors, right? To these meninges, right? It's the denticulate ligament which causes that to happen, helps provide support, and structural support, and kind of secures the spinal cord in its space. A couple other structures, right? Posterior median sulcus, central canal, anterior median fissure. Those we're going to look at here in just a minute on this next slide. All right, so when we just take a cross section, right? Take the spinal cord like here. Right? On the next image, that's where we're going to start to point out all of these different structures, right? From this butterfly-shaped thing to this kind of big football-shaped thing here. That's what we're going to take a look at right now. So all these different structures, when we look at this, here's the spinal nerve. Right? Same thing as right here. We saw this spinal nerve. Right? That's all we're looking at right here, spinal nerve. I mentioned the spinal nerve is the combination of the ventral root and the dorsal root. And they combine to give rise to the spinal nerve. Now here, anterior root, ventral root, same thing, your choice. Same thing, posterior root, dorsal root, same thing, your choice. Now, one of the things about the ventral root and dorsal root is they both carry different types of information. Last presentation I had mentioned how there's some neurons which carry sensory information. There are some neurons which carry motor information. Touch something. Alright, how did you know you touched something? Because little touch receptors in your finger were stimulated. Push your finger into the table. Alright, you can feel the hardness of that table. The reason you feel it is because the touch receptors or touch detectors were stimulated, and they then sent little messages to the brain. Right? That is sensation. Right? What your brain then decides to do with it, right? There is that's what is carried via the motor neurons. Right? For instance, you put your hand in a cold thing of water. I don't want my hand in water. Okay? My brain then, via motor neurons, causes the muscles of my hand to pick up the hand. It's not only the muscles that you move though, right? Even different glandular secretions, right? The release of epinephrine or adrenaline, for instance, the release of different hormones, right? The dilation or constriction of certain blood vessels, right? Those are all different examples of what motor neurons can achieve. So in the dorsal root carries sensory information. Whew, that is neater than my actual handwriting. I'll take it all day long. Right, the dorsal root, right, carries sensory information. So what does that mean? Well, if it's sensory information, which direction is it going? Is it going from the spinal cord out this way? Or is it going from out this way, from the hand, from the foot, and into the spinal cord? Take about 10 seconds to think about it. Right? Which way is it going? Right? If it's sensory information, it would make no sense for sensation to travel away from the spinal cord. Right? Remember how I mentioned the previous video? Our brain is, I say dumb, it's not dumb. It just needs to be told everything. So therefore, it can then make a decision. Right? So all these different sensations, touch, temperature, vibration, etc., they have to reach the brain in order for your brain to be able to make a decision upon them. Right? Think of a CEO of a company. Right? Are they involved with trucking, manufacturing, marketing, right? Delivery, the warehousing, all that kind of stuff. I mean, not directly. Right? They are told all of that stuff from their subordinates, from other whatever, vice president, other managers of those particular departments. Then the CEO makes a decision based upon what those different managers have told him. Same thing with the brain. Your brain makes these decisions based upon what these different sensory receptors are telling it. Right? So those sensory receptors enter into the spinal cord via the dorsal root. Where the synapse is right here. It's something called the dorsal gray horn, or the posterior gray horn. Choice is yours, same thing. The ventral root, again this here, that carries motor information. So that means right from the brain. So we draw brain, cerebellum, medulla pons, not a horrible brain, that's not very good at all, but that's okay. Right from the brain, right, that motor information travels down the spinal cord, down, eventually exits what's called the ventral gray horn, exits the ventral gray horn, and exits via the ventral root. That ventral root then enters into the spinal nerve. Right, remember, the dorsal root plus the ventral root gives rise to the spinal nerve. Right. So, here, posterior gray horn, here is the anterior gray horn, or the ventral gray horn. This right here, it's not near as pronounced, but this is something called the lateral gray horn. The lateral gray horn. The lateral gray horn actually controls the motor nuclei for the autonomic functions. Remember the last presentation, or last video, the autonomic nervous system, that kind of controls all of the automatic functions in the body. Make a fist right now. Right? Clench your teeth. Stand up. Right? You control all of that. You dictated all of that. Alright, take a sip or a bite of something. Swallow it down. Okay, you control this biting and the swallowing part. But when your stomach is digesting it, when your intestines are digesting it, you didn't think about any of that. Right? When you go exercise, what do? You start to sweat. Do you physically cause yourself to sweat? No. I physically cause myself to sprint or to run or to move, but you don't actually think about producing sweat. That's all achieved via these autonomic, is achieved via the autonomic nervous system. The nuclei, or the parts of the spinal cord where those motor neurons leave, is here in the lateral gray horn. So some other things that we see. There's kind of a bridge from here to here, this in between. That's something called the gray commissure, right? All of this in between, that's called the gray commissure. That's the gray commissure. That's on the way first. Again, gray commissure. There's a hole in the middle. Something called the central canal. Something called the central canal. Again, CSF, right, blood vessels travel down through the central canal. These out and through here. These are what are called the anterior white columns, or the ventral white columns. Right, the white columns, are they white? Why are they white? Remember, myelin is almost purely fat or lipids, and fat has a whitish appearance. Right, think of the fat you've seen on a steak, a burger, chicken, pork, whatever it happens to be. It's white. So that's why the white columns are white, is because of the abundance of myelinated axons. Because what actually happens, let's call it sensation, travels in through the dorsal root into the dorsal great horn. Then does it just stay in the dorsal great horn and then travel all the way up to the brain? Nope. Depending on what type of sensation it is, it enters into the spinal, the white columns, and then from there, let me just draw the brain real quick. Well, this right brain. From the white columns, then it travels up to the brain. Right? It travels to the brain via these highway systems, not in the gray matter. Right? It does so via the lateral, or it does so via the white columns. And depending on what type of information it is, or what type of sensation it is it temperature? Is it touch? Is it vibration? Is it pain? Right? That dictates what part of the white columns is it going to travel in. Is it going to be the dorsal white columns, which are all back in through here? Is it going to be the lateral white columns, which are all out to the side here? Or is it the anterior white columns? Again, I don't care that you guys know which sensation travels where in the spinal cord. Nope. A couple other structures. Or the anterior median fissure. This big crack here. Very large, very pronounced. Whoa, that was atrocious. This large crack through here. Again, that's the anterior median fissure. Very deep. Posterior median sulcus, very shallow. Very shallow. Right, the anterior median fissure, you can literally kind of separate and see this really large crack or crevice that you can stick your finger into. Posterior median sulcus is just like this little, almost like, kind of this little kind of divot, this little not culvert, this little ditch, if you will. Right, it's not terribly deep. So this is an image of, again, how I mentioned the different pathways. Right. They have different names. I do not care that you guys know the specific names. But on the previous slide, when I had mentioned how sensory information goes into the dorsal root, synapses into the dorsal gray horn, and depending on what type of sensation it is, it travels into the lateral or into the white columns, and then goes up to the brain. Awesome. So depending on what type of sensation it is, I had mentioned that dictates what highway system it can travel in. All right, think about, certain highways have like specialized lanes for carpooling. All right, so yeah, depending on your situation, depending on what kind of car you are, or how many people you have in the car, that dictates what lane you can be in. Kind of the same idea here, right? Depending on what type of sensation you are, that dictates what lane you enter into. I mean, that dictates whether you enter into this lane and go up to the brain, or you enter into this lane and go up to the brain, or you enter into this lane and go up to the brain. It's all dictated by that. Now, how I'd mentioned, right, this here against sensory tracts and then motor tracts, right, these would be on both sides, right? These blue would be on this other side. Same thing with the red, would also be on the other side. But there's two separate tracts, right? The motor tracts, motor neurons are descending. In the sensory tracts, they are ascending, right? Ascending up to the brain. The motor tracts are descending from the brain. Right, does that make sense? A structure I forgot to point out on here, on this slide, is this structure right here, the dorsal root ganglion, or the posterior root ganglion. Whatever you want to call it, your choice. The dorsal root ganglion. A ganglion is just a bunch of cell bodies located in the peripheral nervous system. The dorsal root, ganglion specifically, is very important in our ability for our autonomic nervous system to function. Right? Think of it this way. Depending on what type of sensation it is, let's just say it's pain or it's temperature. I step on a tack. I'm not going to go into reflexes, right? That whole process of a reflex, because that's much different than a just normal, typical muscle movement. But if we step on a tack, if I step on a Lego, good God, if I step on a Lego one more time. When that happens, what happens? All right, you pick your foot up, but your heart rate starts to elevate a little bit. You get irritated. Your breathing rate starts to elevate a little bit because there was a small amount of epinephrine being released or adrenaline being released. Depending on pain level, right, there might also be like different things called enkephalins, which are released. But how did that happen? Right? Let's just call it pain. Right? That sensation traveling into the spinal cord. One of the things about the dorsal root ganglion is that the nerves, or the neurons which carry that sensory information into the dorsal root, synapse. What does that mean? That means they basically join up with a second group of nerves, or a second group of neurons. Those second groups of neurons then travel into the dorsal great horn. And why does that happen? Because this allows the body to integrate this sensation much more effectively, much more quickly. Right? Because what happens if this pain stimulated a reflex and I needed epinephrine to be released immediately? Well, even as fast as neurons travel, right? If the dorsal root ganglion didn't exist and we weren't able to, include other areas of the spinal cord, we'd have to wait for this sensory information to go into the dorsal great horn, into the white column, all the way up to the brain make its decision, and then back down the motor tracts, and then out to the ventral root, and then outward. Like, that would just take forever. Right? Granted, it would still only take, a second, a couple of seconds, which may not sound like much time, but I mean that's the thing. You being exposed to a flame for greater than a second, you can cause significant amount of damage. So a second is really not that long when we're talking about nervous tissue and nervous system. So that's the importance of the dorsal root ganglion, right? Is to allow for the body to better integrate this different sensory information. So this picture here, as I had mentioned, it depends on what sensation it is: touch, temperature, vibration, pain, etc. But there is a specific part of the brain. It's not like, okay, these random sensory receptors in your fingertip go to some random part of the brain, and the brain says, "Oh, okay, that's what this is." It's not some random part of the brain. There is a specific part of the brain. Right? Let's just talk about my index finger. Right? Take your index finger and just touch the tip of it to the tabletop. All right. There is a specific part of the brain. I'm going to draw a dot right there. Right? Which I'm also going to draw a dot right there. They correspond. Those dots. Let's just say those dots are in the same area. All right. Fingertip. Poke the table. That sensation goes in through the neurons, enters into the dorsal root, bypasses the dorsal root ganglia, into the dorsal gray horn, into the white columns, up through the spinal cord, keeps going on upwards, 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 right? Upwards, 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 and eventually it goes to that one specific part of the brain. And your brain knows, well, if that specific part is stimulated, that when it's stimulated, that's what tells the body, that's what tells the brain, hey, something is touching me on my fingertip. Right, does that make sense? Now there is, right, we didn't go into all of these. For instance, when you look at this here, like, well, wait a second, this goes off like to the side here, right? We see this, all of this stuff going on here. I'm not going to talk about any of that right now. Right? There is so much more. The nervous system, or the brain, is so much more complex and convoluted than just, what I explained to you. There's a slide, I don't know if we'll get to it today, but when we look at the different tracts and look at the different highway systems and the different networks that exist inside of the brain, right, it's almost kind of shocking, right? So these next two slides, right, I'm just going to kind of briefly introduce kind of how complex that is, right? All of the different brain structures which are associated with different movements or with different, sensations. Right? So here, the sensation. Let's say if we back up for a second. What we'd see here, right? Think of it this way. Stand up. When you stand up, take your left arm and kind of stick it out to the side. And now put it back down to your, to your side. Now, when your arms are to your side, think about where your center of gravity is. Right? Your center of gravity, it lies about in the middle, about where the spinal cord is, but it lies somewhere in the kind of the middle of your chest, right along the midline, along the sternum. Is you take, let's say, an arm, and you abduct your left arm out to the side. Your center of gravity shifts to the left side. Right, so now instead of being over the sternum, it shifts over the left, the left breast. So you should fall over to the left, slowly but gradually, slowly and gradually, but you don't. And why is that? That's because the muscles on the right side of the body contract and draw your center of gravity back to midline. You're like, well, I didn't think about any of that, and you were 100% correct. You didn't think about any of that. You didn't think about, oh man, my left arm's sticking way out to the side. I gotta contract my muscles on the right side of my body. Now, let's say if you bend way over to the left, you kind of naturally, for instance, let's say if you bend way over to the left, you might stick your right leg out to the side to help kind of counterbalance that. When it's really large, gross movements like that, then you notice them. When it's small little movements, you don't notice it, but it's still occurring, right? And the reason why that can happen is because of the involvement with so much of the brain. So this is just one kind of example of some of the different parts of the brain that are involved, right? As that information comes up, enters into a part of the brain called the cerebellum, or the cerebellum interacts with something called the pons. The cerebellum then has input up through the midbrain, thalamus. All of these things are structures that we're going to talk about, right? But the idea that this sensation just only goes up to one part of the brain, no, that is could not be more incorrect. Right? This is just one small example how it goes from the cerebellum. There's also input from the pons. The cerebellum has input up to the midbrain, from the midbrain up to the thalamus, from the thalamus up to the actual sensory cortex. And that's just for one sensation. Right? And there's thousands of different, every second your brain's being bombarded with millions of different impulses. Right? So this slide here, right? On this image, they've actually kind of dissolved the gray matter. You're just seeing some of the white matter, which is left. Right? These are different, right, nerve tracts. Think of highway systems. Right? So, I mean, the different highway systems, I mean, you can't even follow anything. But let's just say if I follow this. All right. So there's input from all of through here. You can see all these different collaterals, all these different branches which feed into it. Right? From here, it goes up. Here. It comes up. You see input from here. It comes down. Input from here. Right? I mean, it is unbelievably complex. Right? And that's just, I mean, that's the reason why people with brain injuries, that sort of thing, can present so differently, because there are thousands of different highways or different tracts, and they all accomplish different functions and different feats. Right? So that's where somebody who has difficulty making a fist, the issue could be in the brain, the issue could be in the muscle, the issue could be in the neck, the issue could be in the brachial plexus. There's so many different places the issue could be. Kind of similar idea as far as in the brain, because of the complexity of the network of neurons and tracts and highways in the brain. So, right, by no means, you aren't meant to like memorize anything in particular from this particular image. It's just when you look at the different tracts, some of the different highway systems, it is immensely complex. So now, once we finally reach the brain, right, all that sensation, let's reach the brain. Cool. The first thing we're going to look at is the cerebrum. Cerebrum, by and large, right, is really what we all think about when we talk about the brain, right? 80% of the brain, 80 plus, is the cerebrum, right? All this orange here is the cerebrum. There's different structures that we see. Right, this middle part here, this is a bridge, right? There's a left and right hemisphere of the cerebrum. Right here, anterior view, so looking at it from the front, here is the right hemisphere, here's the left hemisphere. This division between the two, this is something called the longitudinal fissure. Longitudinal fissure. But the bridge between the two, the connection between the left and right hemisphere, is this structure right through here that I drew a line across. That's something called the corpus callosum. The corpus callosum. That is the bridge between the left and right hemispheres of the cerebrum. So again, just like on this picture here, right, that kind of crevice between the two, that is the longitudinal fissure. You can see it here as well. Longitudinal fissure. It goes all the way, oops, got a little off track there, all the way back. All the way back. So the brain is broken up into different lobes. Right? And different lobes have different responsibilities. Right? We'll talk a little bit about some of those a little bit later on. But the frontal lobe, like this here, frontal lobe. That's the frontal lobe. Right, the frontal lobe, that's kind of like what makes, well, oversimplifying it probably, but it's really what makes you, you. Right? Think of, if you're into like The Walking Dead, if you're into like zombie movies, right? Zombies are kind of like frontal lobeless, right? Your frontal lobe is literally what kind of gives you personality. It's where you create opinions. It's where you create conversation, ideas, right? That's where it all comes from, is the frontal lobe. A couple other things that we see, right? This blue, there's something called the parietal lobe. The parietal lobe, right? Your parietal lobe has a lot to do with speech, or speaking, speech recognition, as well as language, right? Development. Occipital lobe, right? The posterior, right? The very back of the head, right? That deals with vision. Some of the other things that we see, right? When you look at the brain, it kind of looks all squiggly, right? For instance, I go to this next one, right? It looks all kind of squiggly, and the reason why that is, well, let's back up. These are called gyri, right? Those squiggly worms are called gyri. The cracks in between are called sulci. So here's a big one. This crack here, that's sulci. Sulci. So I guess I should probably do it on the actual sulci image. Sorry. Sulci. Right? Anything that you see that's like a crack and crevice like this are sulci. The ones I'm pointing out are just quite large. Right? Any of the worms, the wiggly worms that you see, those are all gyri. It's all gyri. Now, any ideas why that exists? I'll jump to this picture and just kind of leave it here for a second. Any idea? Take another 8 seconds. All right. So, this outer perimeter, go all the way around, but this kind of brownish beige up and through here, that's the cerebral cortex. That's the cerebral cortex. This darkish brownish, outermost layer here. That's the cortex. So, for instance, a few slides ago when we talked about this sensation, the sensation comes into the spinal nerves, goes into the spinal cord, travels all the way up through the brain, and it goes specifically, for this example, specifically to the area where, when it's stimulated, the brain knows that something's touching my fingertip, for instance. Yeah, that specific point that we're talking about, that exists within the cerebral cortex. Alright. So, the primary reason, or the reason, right, why we have these gyri and sulci, we have to be able to maximize how much cortex there is in the brain. Right, there's only so much space inside of the brain, even if you have as big a head as I have. Right, my wife reminds me all the time, your head's huge. Thank God our kids didn't have big head when they came out. Like, all that sort of stuff. But there's only so much room inside of the brain. Or let's try that one again. There's only so much room inside of the head. So in order to maximize how much cortex there is, the brain has these gyri and it has these sulci, so therefore we can maximize how much cortex there is. Right, for instance, we just measure this, right? If I just measure it, we haphazardly, let's say an inch, 2 inches, 3 inches, 4 inches, 5 inches, 6 inches, 7, 8, 9, 10, right? Because of the gyri and sulci, I've maximized how much surface area or how much cortex I could possibly have. So if I were to measure from here to here, that might be 5 inches, right? From here to here, it might be 5 inches. But because of the gyri and sulci, I'm able to have, again, significantly greater amounts of cortex. That's the purpose behind the gyri and the sulci. Right, does that make sense? Another structure that we see here, again, we saw it before, is right in through here. Again, take a second to think about it. But about 2 minutes ago, I pointed out that structure. This is the right cerebral hemisphere. Here's the left cerebral hemisphere. This is the bridge between the two. This is the corpus callosum. The corpus callosum. So here's an image of kind of the brain from a lateral view. Again, we see some of the lobes, as we saw before, right? The frontal lobe, right? We saw the parietal lobe, we saw the occipital lobe, excuse me. We didn't see the temporal lobe before because we looked at a superior view. But when we use a lateral view, we can see the temporal lobe. Right? Right in through here. There's also a lobe, something called the insula. It looks kind of like, it looks like this because you actually have, it's deep. You have to actually separate. There's something called the lateral sulcus right here. And in order to see the insula, you actually have to separate. You have to pull down on the temporal lobe. You have to pick up on the frontal lobe. And as they separate, then you can see the insula. All right. There's kind of two gyri, which are tremendously important. They're all tremendously important. But two which are the kind of the primary means by which we can feel and move. That's right here. Right, when we look at this, see this gyri right here? This one right here. Do you see how they run pretty well kind of parallel with each other? Right, when you look at the rest of them, if I just kind of follow this one here, for instance, it doesn't really follow suit with anything around it at all. The same thing back in through here. Or they don't really follow suit with one another. When we look right here, this is kind of hard to follow. Sorry, let me get some of these out of here. You see how these two gyri kind of run parallel with each other? That's how you can differentiate. That's how you recognize, oh, that's where the precentral gyrus and the postcentral gyrus exist. That's where they are. The precentral gyrus. Now, the reason why it's called the precentral gyrus, there is something in between them. The sulcus. Right here. So there's a sulcus in between them called the central sulcus. Let me just erase all this stuff, get it out of the way. So, right here is the central sulcus. This way is the frontal lobe. This here is the precentral gyrus, right? Oh shit, let's see. I forgot I could do that. Oh, you monkey. Let's try that one again. Alright. Alright. So, central sulcus right here in the middle. This is the precentral gyrus. This is the primary motor cortex. When I say primary motor cortex, yeah, make a fist. Right. Stand up, right? initiation of that movement began in the motor cortex. It began at the precentral gyrus. All right. From the central sulcus posteriorward, that's parietal lobe. In this first gyri right here, that is the post-central gyrus. That is the what's called the primary somatosensory cortex. You're like, well, what the hell does that mean? It's your sensory center. Right? We looked at that a minute ago. This thing here, right? This, the feet, the arms, the hand, the face, right? This specific part of the cortex we'll be looking at, that is the post-central gyrus that you're looking at. But it's from the side, you can't really tell. But that's the post-central gyrus. That's what we're looking at right here. Whereas you can see the face here, come up with the hand and the elbow, the knee, etc. Right in through here. That's where that exists. Now, first off, no, you do not need to be able to recognize or understand all of these different numbers and what they do. Right? There's different numbers that correspond with different functions and areas of the brain. Not at all. However, it is important that you do recognize some of the things that I point out to you. For instance, like the primary motor cortex, that being the precentral gyrus. The post-central gyrus here, that being the primary somatosensory cortex. The occipital lobe, how I mentioned that was your occipital lobe, that's how you are able to see. That's the primary visual cortex. In the frontal lobe, the prefrontal cortex, I mentioned the frontal lobe is kind of what makes you, you. That specific part of that is the prefrontal cortex. That is what makes you, you. That's, I think if you didn't have that, you'd kind of be like this, zombie sort of thing. So it's important from that standpoint, right here, along the temporal lobe. You see auditory association area. When I say association area, yeah, think of it this way. I'll use visual association area. Visual association area makes a little more sense as far as example-wise. You go to a mall, not now, but when they were open, or a large group of people, 1,000 people in a group, and you're just walking around, and all of a sudden you somehow pick out that one person you know out of 1,000 people. How do you do that? That's in part because of the visual association areas which exist in the brain. Our brain is so interconnected, How this picture here, from the occipital lobe, way back in here, there's all these different projections, which some even project to different memory centers of the brain, which are way up and through here. Why? Because where do you house, the people you know, your ability to recognize them, your ability to know that you know them, that's all housed in your memory center, So that's just one example. That's just one example of how your brain can, for instance, recognize somebody and that you know them out of a group of 100 or 1,000 people. So it's enormously complex as far as what the brain is able to do. We see Wernicke's area, Broca's area, Broca's speech area. These are different areas of the brain which, function for language and speech. You think about it, your ability to hear somebody, your ability to hear somebody, that's completely different. But your ability to process that information, that's a totally different. So that's what we're talking about as far as Wernicke's and Broca's. Your ability to process what that person has said to you, and then your ability to produce and generate a response to it. There's different areas of the brain which are involved with different functions. Just like there are people who might not be able to say a random sentence, for instance. If you ask somebody, hey, how you doing today? Oh, I'm doing well. They might not be able to respond that way. However, they might be able to sing a song that they remember from their childhood. And why? Because the memory center, you're not having to think and to process a specific thought. Right? You're not having to generate the response. The response is there. It's the song. You're just simply, eliciting the memory of it. Right? So that's one thing with the brain. Right? When I go over the brain, whether it's here in lab or in lecture, right? Pay attention to the specific things that are being talked about. And the reason why I say that is because the brain is unbelievably complex. I've said it 9 times, and I'll say it a 10th. Right? If you look up, for instance, the pons, which is a structure we're going to look at here in a minute, or if you look up midbrain, if you look at the pons, you're going to have a list of 35 different functions that come up. However, there's like 3 or 4 which are kind of the primary functions of the pons. Those are the ones you want to pay attention to, the ones that are talked about in class. It's not to say that, oh, well, I thought it was involved with all these other things. It is, but it's much too complex. It's much too convoluted. Just like in math, you can do all sorts of things with numbers. Right? My kids are 7 years old, and they are learning math. Right? Numbers, you can take it all the way up into do physics and things like that, but I don't explain that to, I don't explain how to do physics to them, because they're not there. They don't need to understand that level of math hierarchy, if that makes sense. Right? Same thing here. There are, right, here we're just looking at kind of the basic functions of certain parts of the brain. We're not getting into more complex functions. We're not getting into more complex processes, because that's where it just gets very convoluted and very difficult to grasp. This is an image where we can actually see the insula. How I mentioned before, you have to take the temporal lobe, pull it down, take the frontal lobe, pull it up. When you do that, you then expose the insula. Now, here's where we start to, right, we're just covered the cerebrum, right, all of this out and through here. Now we're going to get into kind of a deeper part of the brain, something called the diencephalon. The diencephalon is kind of the group, and there's 3 things which make up the diencephalon. There's the epithalamus, there's the thalamus, and there's the hypothalamus. Right? Hypothalamus, that's this front part. Thalamus is here. Why I'm drawing circles, I don't know. They're already colored. Back here is the epithalamus. Right? They all have different functions. Right? Hypothalamus, hugely related to endocrine function. Right? When we talk about hormonal regulation, we talk about homeostatic balances. Right? Homeostatic balance, that is the hypothalamus. Right? In 122, right, you will talk about that, right, ad nauseum. The thalamus, same idea. Thalamus, very complex. When we think about the thalamus, it's always kind of referred to as the sensory gateway, or the gateway to the higher centers of the brain. And what I mean by that is, let's say your sense of touch. All right, it goes through the whole process of entering into the spinal cord, going from the dorsal root, the dorsal gray horn, into the white columns, and then the white columns, they ascend up the spinal cord, ascends up the spinal cord. Remember how I mentioned, if it was my fingertip, let's just imagine, oh, that's where it's going to end up. The first place it has to go to is the thalamus. Then from the thalamus, then it can go to the somatosensory area. What if it's your, whatever, sense of vision? Alright, you got eyeballs right here. That enters into the thalamus and then projects back to, right, the occipital lobe. The only sense which does not go to the thalamus, right? All of your senses, your sense of touch, taste, temperature, hearing, seeing, vibration, right? right, pain, all of them go to the thalamus, except for your sense of smell. Your sense of smell bypasses the thalamus. Right? This is the importance as to why, right, metal detectors, yeah, why smoke alarms are so important. You're like, okay, that sounds odd. Obviously, they're important for alerting you that there's a fire, right? But really, most, during the day, if you're, right, awake, you'll be able to smell, see, right? Yes, there are obviously exceptions, but you'll be able to see it, smell it. One of the problems with, right, the fact that your sense of smell does not project to the thalamus, there's something called the reticular activating system. That is what keeps your brain aroused. That's what can keep, basically wakes your brain up, right? The other day, well, actually, not the other day because I haven't driven it forever. A couple weeks ago, right? Have you ever just been driving and all of a sudden, like 10 minutes later, you like come to and you're like, oh my God, how did I get here? I don't even remember driving. That's your reticular activating system, which is functional. Like, had there been an accident or had there been a deer or something which ran out in front of the road, you would have reacted to it, right? It's the reticular activating system which essentially arouses the brain, not arousal as in like Marvin Gaye type, let's get it on, not that kind of arousal, right? But when we sleep, right? Well, if we're awake, well, you can smell smoke, you can maybe hear the crackling of the fire, you can see it. All right, when we're sleeping, well, you can't see it, all right, you can't hear it, so you can smell it. Well, no. Part of the issue, right, is your sense of smell, right, will not wake you up, right? So, for instance, because of the fact that your sense of smell does not project to the thalamus, right, you can't actually, right, smell that smoke. That's why, right, fire alarms make this ridiculously loud sound, because that will actually wake you up. But the smell of smoke, that won't, right, and it can't, because it's the reticular activating system projects to the thalamus, and then from the thalamus, it then arouses and wakes up the brain. That doesn't happen with your sense of smell. Right. Your sense of smell, there's different things it projects to, something called the hippocampus, something called the amygdala. It projects to different memory and fear centers in the brain. Really much more of an evolutionary type thing, right? Albeit our sense of smell is not merely what it once was, right? But our sense of smell is much more closely tied to our ability to respond. Let's think of it this way. If I were to see a car accident, if I were to smell a car accident, if I were to hear a car accident, right, like, hear the crumpling, glass shattering, smell it. You hear, smell burning rubber, you smell, right, gasoline, those sorts of things, or if you see a car accident. As far as your body's ability to elicit a sympathetic response, the fastest response would be from you actually smelling that particular accident, right? And that's because your sense of smell, your nose, right, projects directly into those fierce, the memory centers of the brain. It doesn't go to the thalamus, right? Anyways, so if you haven't checked your fire alarms, do so. Make sure you got fresh batteries in those things. Next part. The next part of the brain we're going to look at is something called the brainstem, and there's 3 parts of the brainstem. Right? There's something called the midbrain. That's this guy right here. That's something called the midbrain. Now, actually, I'm going to kind of cover all the 3 individual parts, and then I'll go into more detail. But the midbrain is the first part of the brainstem. Secondly is the pons. Right? The pons is the second part of the brainstem. And then lastly, you have the medulla oblongata. That's the third part of the brainstem. If you've ever seen The Waterboy, right, this is, the part of the brain that makes you ornery, right, as Mama says. If you haven't seen The Waterboy, go reevaluate your life and go watch it. Right? Listen, we all got time on our hands. Right? Actually, come to think of it, that movie came out years before most of you were born, as sadly as that is. It's still a good movie. It still holds up nowadays. So, anyways, here is, again, a gross model of the brainstem. Right? Here, essentially all the way down, it's all brainstem to about right here. Then it starts to morph into the spinal cord. But up in here is the midbrain. Right? The midbrain has a number of different reflexes associated with it. Primarily reflexes for vision, as well as auditory reflexes. Right? The fact that you can, a loud book drops behind you, you hear that sound, you snap your head, your body around to look at where the sound came from. Same thing as where your eyes follow. Right? Same thing with if you're driving down a car, if you're in a car driving past the woods, right? You can't just look blindly off into the woods. For instance, reflexively, we are geared towards like finding something to focus on, right? Going from object to object to object, from tree to road sign to fallen tree to deer to tree to tree to tree to road sign to car. Like, you can't just blindly stare forward and stare at nothing. Right? If you're doing that in a car, you're just staring at the window. Right? If that makes sense. But that's because reflexively, you can't trump a reflex. Reflexes are there, you can't trump them. Good luck doing it. It's the superior colliculus, this thing right here. Right? That's where the visual reflexes of the midbrain are housed. Same thing with the inferior colliculus. That's where the auditory reflexes are housed. Right? Those are both a part of the midbrain. Down here, the pons. Right? The pons. Now, the pons or the basilar pons, right? Choice is yours. Right? You can, whatever you want to call it. Neither one's correct, or neither one is more correct than the other. Right? So, when we talk about, right, the pons, a number of things the pons is going to do, but really the most important thing is the pons is going to help coordinate muscle movement. Right? There's kind of a whole series of tract systems which go back and forth between the cerebellum and the pons. Right? The cerebellum, that's this all leafy looking thing. Cerebellum we haven't talked about yet, but remember the example? Well, I guess we not inadvertently, but unbeknownst to you, we did. The example where I talked about if you stand up, take your left arm, stick it out to your side, and your center of gravity shifts to the side. But you don't fall over. Why is that? The reason you don't fall over is because your cerebellum, again, this guy here, cause the muscles on the right side of your body to contract. So we did talk about it, but we didn't specify it was the cerebellum doing that. It is the pons which coordinates this kind of movement, right? For instance, from the cerebral cortex it comes down, enters into the pons, and then from the pons it then enters into the cerebellum. And then from the cerebellum it exits and then descends down the spinal cord. Right? And the reason we're like, well, that's weird. Why doesn't it just go from the cortex? Let me erase these for a second. Why, if eventually it's got to get down here to the spinal cord, but if I've got to stop by the cerebellum first, why doesn't it just go from the cortex into the cerebellum and then from the cerebellum down this way? Because it's so much more complex than that. Right? With each movement, let's say you're moving, try to move quickly, or you're moving because you're in fear of falling, or you're moving because you're exercising, or if you're moving to catch a baby you just dropped. All of those things are going to elicit different systemic responses. I go to drop, I'm not sure why I'm talking about dropping a baby, but let's just stick with that example. I go to drop a 2-month-old I'm holding. Oh my gosh, they're going to slip out of my hands. I recover quickly and grab them. I then have a small sympathetic response, right? My heart rate elevates, breathing rate elevates, etc. The reason all of that was able to happen is because as it goes into the pons, it goes into the cerebellum as well. But even from the pons, it goes to different parts of the brain, right? Up to the limbic system, up to the basal nuclei, up to different areas of the brain that we haven't talked about, because it still projects to different areas of the brain. So therefore, the brain and the body can have this overall systemic response. So again, that's why I mentioned we're not going to go into the extreme complexity of the brain. It's one of those things where it's unbelievably complex, so make sure to pay attention and focus on those aspects of it that we are talking about. Alright, so the next thing, where was I? Oh yeah. So from the pons, right, beneath the pons, down here, the medulla oblongata. The medulla oblongata. The medulla, this is where it's going to house the cardiac and respiratory reflex centers of the body, right? For instance, if we need to elevate, if breathing rate is depressed, or if, let's say, cardiac rate needs to elevate, that sensation, that sensory information goes into the medulla and it stimulates the heart rate to increase, right? For instance, we haven't covered, I forgot the order switch, we haven't covered cardiovascular system yet. In blood vessels, there's certain blood vessels, let's just say, right, these are the carotid arteries, right? If you're like, carotid arteries, I haven't heard of those. You've heard of the jugular veins. Everybody's heard of the jugular, right? Think of the jugular, but just think of the arterial counterpart. There's little receptors in it that can detect how much the vessel is stretching. If it's not stretching enough, those receptors, those neurons travel eventually up into the spinal cord, into the medulla. The medulla says, hey, you know what? Our blood pressure is not high enough. So the medulla can send an impulse down to, let's just call this the heart. And then the heart responds by increasing the rate in which it's pumping. Right, does that make sense? All right. So next is the cerebellum. Right, the cerebellum. This is this last kind of part right in through here. Right up and through here. Now a couple other things. Actually, I'll cover the cerebellum first, then we'll back for a second. Some of the structures of the cerebellum. Here is, again, we're looking at the cerebellum from the posterior. You can't, unless it's been removed from the brain entirely, you can't see the cerebellum from an anterior view. So we always look at it from from the posterior, from the top and from the bottom. Here's a superior view. This left image. Right, so imagine if I took the brain and cut it off like right here, and I looked at it from the top down. Almost you see that this left cerebellar hemisphere and this right cerebellar hemisphere, there's this bridge in the middle called the vermis. Almost looks like a worm, if you want to call it that. Same thing, I mean, it wraps all the way around. You can even see it on the underside as well. Right here. Something else that we're going to be able to see, and I'm going to show you that, oops, back up to this picture here. There's a few things I wanted to point out on this slide here. You see how there's like these little individual, you're like, oh, those are gyri. Yeah, they're not. Right? These individual things are called folia. Right, here's a folia here, right, folia here. One of the things about the cerebellum, all this kind of white matter going through it, if you kind of look at it, it kind of looks like the veins of a leaf. This is something called arbor vitae. That's something called arbor vitae. Arbor vitae. The cerebellum, as the right, trillions of neurons that the brain, spinal cord have. The cerebellum, right, there are millions upon millions of impulses which are bombarding the brain every second of every single day, from the day, from before you were born to the day you die. There are things called Purkinje fibers. We'll talk about them a little bit in lecture. But your cerebellum, think of it this way. Let's just, if we just look at skeletal muscle, right? There's 700 plus muscles in the body. Any movement, take your left arm and abduct it. Every single muscle in your body has to contract and respond in some fashion. The reason why they can all do that simultaneously has entirely to do with the cerebellum. So the fact that there's so much sensory information and motor information, sensory entering, motor leaving the cerebellum, there has to be this massive amount of white matter which exists, and there is. That's what's called the arbor vitae. Something else I want to point out here. This is something called the fourth ventricle. Right? Later on, it's going to become important when we talk about the cerebral spinal fluid. Right? Same thing with the third ventricle. Right? But this little triangular shaped chamber, right? That's called the ventricle. That one specifically, the fourth ventricle. So here are what I had mentioned, right? Some of the different structures of the brain. How, for instance, when I talked about how from the pons, sensory information, motor information enters into the cell. Sensory enters into the, from the pons, motor information enters into the cerebellum, and then from the cerebellum it can then descend down the cord. Right? That's not the part I'm trying to get to here. I mentioned, there's so many different other parts of the brain which the pons can send motor information to. This is just a glimpse of some of those different areas of the brain. Through here, something called the basal nuclei, right? Globus pallidus, putamen, caudate. These are what help to regulate movement. Now, you're like, man, there's lots of things which help regulate movement. Yeah, there's the motor cortex initiates the movement. The cerebellum makes sure that the movement we're doing is what we're carrying out. The basal nuclei, part of its function is to make sure that we're actually moving how we're intending to move. And part of what the basal nuclei does is it actually inhibits muscles from firing. Right? You want to make a fist, there are certain muscles which need to be inhibited, while there are some muscles which need to be contracted. Right? So it's very dependent upon the basal nuclei. People who have basal nuclei issues have difficulty forming appropriate movements. Right? The thalamus. Thalamus we'll talk about. With the thalamus, the third ventricle, the lateral ventricles, all of those things have to do with the CSF, the cerebral spinal fluid, and the flow of that. So that's where I'm going to end, or about 20 minutes shy. But that's where I'm going to end kind of the class for this week. Right, so now we've seen where these nerve impulses or these nerve messages go. Right? So these sensory neurons are fired, and then that message travels along that sensory neuron into the spinal cord, from the spinal cord up to the brain. Awesome. But what actually generated them to begin with? What actually caused those neurons to fire in the first place? That's what we're going to pick up next class. Everybody take care, and we'll talk to you soon.